Hello, everyone, and welcome back to this DevCon. So I'm actually here to talk about some of the research that we are currently doing within our Secure Systems Collaborative, which includes two labs that I'm a part of, the Cybersecurity Education and Research Center, as well as the Wyoming Advanced Blockchain Lab that is supported by IOHK and state matching funds. So I'm Mike Borowczak. I am the Loy and Edith Harris Assistant Professor of Computer Science, and going to briefly talk about the security and resilience of distributed systems. So our work has been funded by many agencies, National Science Foundation, Idaho National Labs, National Security Agency, Department of Defense, among others. So this work would not be possible without their support, and you'll see where that leads to. In addition, the Cybersecurity Education and Research Lab is built up of many, many people. So we have master's and PhD students and many undergrads, many of which are not listed here. So the IOHK Wyoming Advanced Blockchain Lab also is starting up and growing. You'll see some of our members here, and you'll see them throughout the rest of the conference and many other events. If you see us, reach out, talk to us. We're always looking for more people to join us in our research activities. All right, so let's get started. You've got a system made up of many subcomponents, subsystems, and the question you should ask yourself, should you trust more components or should you have fewer trusted components? So I'll let you take a moment to think about what you might answer there. And well, I'll also say that as designers, we generally should be establishing policies and procedures for the actions that our system is taking. And it's also important to note that when you have a trusted entity in your system, what you're really saying there is that those entities are allowed to violate or act beyond the policies of your system. You trust them to do some actions, right? You're implicitly saying, I trust this module to do blank. And so while it might seem counterintuitive, we actually should be looking to minimize in a system the number of entities we trust. We should be relying on our system design, on our procedures, our protocols, all of these things to actually maintain the properties of our system. We should not be relying on an entire scope of trusted entities who at some point might break our trust. So what we end up doing in a lot of systems is we start leveraging strong security primitives, right? So, I mean, this is not uncommon. You know, think cryptographic algorithms, think trusted hardware modules. We could have a really long debate. Luckily, right now, this is a pretty asynchronous one-way. Now, at the end, you can maybe debate this in the Q&A session, but we could debate whether or not you should spin up your own cryptographic algorithms from scratch. And I'll just say right now, what I tell students in my classes, 99.9% of the time, a developer should always answer, no, I'm not going to respin up a strong primitive that has already been designed. So, you know, we have ways that we can measure the theoretical security of the functions of the primitives that we have. But you should start asking yourselves, what happens when we take these primitives that we can, you know, we can assess, and we start implementing them in hardware, right? So massive server farms, you know, individual laptops, get smaller, cell phone, okay, some kind of really lightweight communication device like a garage door opener, or a smart card. What starts happening then? Well, what we care about, part of the Cybersecurity Education Research Lab cares about is what happens when you implement these functions in the real world and a real target. Well, they start requiring resources that we can measure. They start producing byproducts that we can measure. And these byproducts can be used to actually extract information. So from physical implementations, we can start to extract keys, for example, from our secure primitives. So actually we have AES down here. We can identify individual operations. We can identify individual bits of keys. And you can do this too. You can go out and buy yourself a chip whisperer for couple $100, and you can start breaking your own hardware. It's actually pretty easy to do, and it has a Python programmatic interface. So this is not unattainable even for an average attacker. So what do we start doing? Well, we start making things better in hardware by basically improving how we design our silicon. But unfortunately, everything has a trade-off. If you want something secure, you're going to have to pay a penalty. Just a really quick takeaway from this, we found that in order to enhance security, we roughly approach a doubling in size of our hardware layouts. Not ideal. There are some potential added benefits. We also end up having a huge amount of power increase, but we get some security out of that. So assume that we can secure a system. Now let's assume that we want to use many of those, right? Because our world is comprised of systems that are, well, interconnected. So we're going to look at an example through some swarms of agents. It's hard to maybe see down there at the bottom, but you basically have these agents circling a target. Many agents, same behavior. And just so you can see some tracking, here are those agents tracking around. We can do this in 2-dimensional spaces or in 3-dimensional spaces with targets that are static or moving. So we have a secure hardware device, and now we've used this secure hardware device in some larger collection. So the question is my larger system now resilient? I've protected it from attack at a low level. Is my larger system protected? This is actually some details that these agents are using some really simple rules. But let's look. Are my agents resilient to attack? So here we go. They've circled it. I've got an evil attacker that is somehow wiping out half of my agents. And it appears that my process is resilient to attack from basically getting blasted away. So are we good? Do we have a secure, resilient system? Well, unfortunately, no. We've made some really bad assumptions. So here we have a system, and now we have an intelligent attacker that understands our system, and they're able to manipulate and somehow open up a region of this target. You might be asking yourself, why does this matter, right? How does this impact my future designs? Well, there are solutions, right? If we avoid the fundamental assumptions that all of these distributed systems or any system we have follows the properties that we have made, and all we care about is our own designs, we are in trouble. So here is the point, and I have rushed through my presentation at blazing speed, hopefully for some Q&A. But here is the big takeaway. A lot of times you will hear people say trust but verify, and I actually, while I've said this in the past, I actually disagree. Really, you should focus on minimizing your trusted components. You need to focus on creating incredibly strong policies and protocols and procedures within your design. And you need to assume the worst. Assume that your enemy knows your entire system. So this is a reformulation by Claude Shannon of Kirchhoff's principle. But your attacker doesn't care how you designed your system. They care about what your system can do. So they probably honestly know your system better than yourself, just because they have looked at your system in ways that you never have. They are looking to leverage everything they know about it to manipulate the system in ways that you never thought possible, because you were focused on your particular design case as opposed to what the capabilities of your system were. So that's why the Wyoming Advanced Blockchain Lab, through funding from IOHK, is looking into one of its research projects to probe how existing authenticity validation mechanisms, like how they actually work. And we're looking to find limitations and vulnerabilities of basically the weakest link of the system, which happens to be these ultra low power, lightweight, low cost hardware devices. We make some broad assumptions on how these devices can be used in a larger system. And we need to validate that we truly understand these systems and how they're implemented. So we are also concurrently defining protocols that don't implicitly trust the hardware agents they come in contact with, right? So we are no longer going with that root assumption of trust but verify. We're going with a we don't trust anyone approach. So with that, I'm going to open it up for some Q&A. And at the same time that we do the Q&A, I'm also going to tell you that we are looking for those of you that want to continue your education and research with us. So apply to the University of Wyoming and join us in the Secure Systems Collaborative. So our CEDAR Lab and IOHK funded WABL Lab are both looking for master's, PhD, and postdocs. So if you are interested, if anything I talked about, or as you talk to other members of the lab throughout the next month or so, if you're like, hey, I really want to work on the work you're doing, we'd love to have you join us. So with that, we do have plenty of resources, but I'm going to go back to the Q&A slide and see what we've got going on. I do see a question about being able to access the presentation that was posted. I will make sure that that goes out. It'll be posted on our Secure Systems Collaborative site for sure. And I'll talk to the organizers of DevCon to see if they'll also post it. But our website is uwy.edu/S2C. So letter S, the number 2, the letter C. And we will we'll make sure that all of our presentations that we have are linked off of our sites. All right, I'm not sure if there are any questions or if there's anything that I can do to see other ones, but let me, I guess, put up our contact information, and you can reach out to us anytime. So let me make sure that gets up there for you. All right, so our contact information, there's the website where we will post all of our presentations, website links to both CEDAR and IOHK research labs, and my direct contact information should you like to reach out to me either now or in the future.